Now we have calculated the loading, minimum steel, okay. We have finalized the slab thickness, effective depth in short and long direction. Now we will go for the moments, and for the moments we have to use the ACI coefficients. So here panel 1 in X direction means panel Y in Y direction. Here panel 1 in X direction, panel Y in Y direction. We have to design this slab panel in both directions due to the two-way slab action. So in the short direction, the value of Lx, that is 4500, and in the long direction, that is 7000. Here. And our M value, that is we have approximated to 0.65. And case 4, in the short direction, that is 4500 millimeter, our D value will be 123 millimeter. And now we will go for our case 4, and we have to pick the coefficients. Okay, our case is M value 0.65 and our case is 4. So here our case is values M value 0.65 and our case is 4. So here you can see these two values we will pick in the X direction and in the Y direction. X direction 0.063 and in the Y direction 0.011. Now the ACI coefficients for dead load. Now for live load positive moment, here our case is 4, 0.65. so here that will be our coefficient. In the Cx means in the X direction, in the Y direction. Now the last table, that is ACI negative moments, coefficients for negative moments in the slab. So case 4 0.65, 0.65, case 4. Here is the table that cell that we will follow. Okay, so these three coefficients we need from the three tables depending upon the case. Okay, so here first of all for positive dead moment, so our Cx mean the X direction coefficient is 0.063 and in the live 1.66 live load, so that is we have already calculated 1.6 L 3.14 and dead, that is 7.45. L is the shorter span, we are discussing in the shorter span 4.5. so what is coefficient, that is for dead load, for live load, so that is 0.063 and 0.078. let's go check. Okay, you can see 0.65 and again Cx is in the X direction, that is 0.063 for the dead load. For the live load, that is 0.078. okay, so here 0.063 and 0.078 for dead load and for live load, 9.51 and 4.96. so now sum up all the positive moment, so your total positive moment, that is 14.47 kilonewton meter. So that is your total positive moment. So our total load, that is a 10.59. so now we will see the negative moment. We have negative moment for the combined load, not for the separate load. So as I have discussed, that we have the negative moment coefficient for the total load, so that's why that is QU 10.59. so now I will go for the negative moment coefficient 0.65, that is 0.077. so here I came back, so that is value 0.077. so our total positive moment here and our total negative moment here 16.59 kilonewton meter. So here if we got the moments, now we can calculate the steel. Now we have positive moment, we have negative moment. Okay, so now we can calculate its area of steel. So for calculating of area of steel, you can use the same exact formula. Okay, that is 0.85, Fc prime is 18 divided by Fy, that is 280, multiply by bracket open 1 minus under root 1 minus bracket 2.614 multiply with moment, that is 14.47 10 power 6, okay, divided by Fc prime, that is 18, multiply by BD square 1000, multiply D in the smaller direction, that is 123 millimeter square. Okay, here you will bracket close, enter. Okay, you are getting the raw value, means steel ratio, that is 3.9366 10 raised power minus 3. So multiply with BD to get the area of steel, that is B, multiply with D, that is 123. You are getting the total area of steel against positive moment, that is 484 millimeter square. Here the author has calculated by the from the table formula with the positive moment, that is 492 millimeter square. So with the exact formula, that is the 484 millimeter square. So you can use the exact formula instead of going for the tables or the approximate. You can use the same exact formula for the calculation of area of steel. So for the, let's see, for the negative moment, so our negative moment is 16.51. Here author has calculated for the negative moment area of steel, that is 566. We will go back. Okay, in this equation we have to only put the moment value, that is moment value is 16.51. 16.51. okay, hit enter. You are getting this value of steel ratio, multiply with BD 1000, multiply with 123 equal. So your answer is 555 millimeter square. So that is the area of steel from the exact formula. So you got the area of steel. Now you can provide the die of bar and at what die of bar and at what spacing. So for spacing, definitely you have to follow the criteria. So here number 10 at 140 millimeter center to center, and for 566 again. So let me show how the author has provided. So I will come back at 236. Now I am going at the end of this book. Here is US customary bars that is mentioned by this at the start of the example. So if we provide number 10, okay, 10 bar whose area is 71 millimeter square, so required is required is 484. So 71 divided by 484 multiply with 1000. That's how you will calculate the spacing. So here is spacing 146. So round it down to 440 millimeter. So that's how the number 10 at 140 millimeter center to center is calculated. So I will again go back the same page, 236. Okay, here number 10 at 140 millimeter center to center. You can check the spacing criteria, that will also satisfy. So again our calculated area of steel is greater than AS minimum, so that is okay. So our negative moment value is 566. You can again calculate the spacing. Now I have, that is we have calculated 555. So we can provide number 10 at 120 millimeter center to center. Okay, so here, so again our area of steel is greater than AS minimum, and that is okay. So that is, we have calculated the area of steel in the x direction for the positive moment, for the negative moment, here and here. Okay, now same panel 1 for the y direction. M value will be same, case will be same, only D will change. Okay, D and span length. Our in the span length in the x direction, that is 4.5, and in the y direction, that is 7 meter. Here, that is panel 1 in the y direction. M is same, case is same, D will be changed due to in the y direction the that is our you can say the distribution bars. So that is the effective depth that I have calculated at the start, that is 112 millimeter. So same way we will pick the coefficients, positive dead load coefficient, positive live load coefficient, and negative moment coefficient. So here 0.011, 0.014 and 0.014 for the negative. So let's see the coefficients in the coefficient table. Here for positive dead load, that is 0.011, for live load 0.6, 0.014, and for the negative moment the coefficient is 0.014. So here you can see, after putting the coefficients, we got the positive dead load moment, positive live load moment. Okay, span length is 7. So total moment, positive moment, that is 6.18 kilonewton meter, and negative moment, that is 7.27 kilonewton meter. When we got the positive moment and negative moment, now we can calculate the spacing, area of steel, then spacing. Okay, so here for the positive moment, okay, the moment value, that is the moment value is 6.18, 6.18, and D values also will be changed, that is 112 millimeter square. Rest of the formula will be same, equal, we got this value for the steel ratio, multiply with BD 1000. Here BD is 112, so our answer is 22 millimeter square. The value we got of area of steel, that is 222 millimeter square. So here the author has calculated 280 millimeter square, that is somewhat bigger. So but I have checked the detailed calculations, this value is wrong. So this value is right, that is 222 millimeter square, but this area of steel is less than AS minimum. Our AS minimum, that is 300 millimeter square. So that's why we will provide the or use AS 300 millimeter scale. So when we use the AS 300 millimeter scale, so our spacing comes number 10 at 2 to 5 millimeters center to center. Same way that we have calculated in the previous panel 1 X direction, 71 divided by area of steel 300 multiply with 1000. Our answer is 236 millimeter square. So round it down to 2 to 5 millimeter, or you can also round it down to 230 millimeter center to center. That will be okay. So again you have to check the spacing criteria. So now that is for positive moment. Similarly for negative moment, that you can check and verify. So for negative moment, area of steel, that is 280 millimeter square. So you have to that is again less than AS minimum. You have provide the AS minimum area AS minimum 300 millimeter square, and the spacing come with 300 millimeter square, that is 2 to 5 millimeter. So that is our panel 1 X direction and Y direction area of steel is complete. Okay, for positive moment and for negative moment. Similarly we will perform for other panels. Okay, here panel 2 M value is 0.85 and case is 9, and in the X direction, if our that is the short span, so that is 123 millimeter effective depth. So for the coefficients for panel 2, for dead positive, that is our case is 0.85, case 9. So here I have opened the design aid. Case is 0.85, M value is 0.85, case is 9. So these values for live load 0.85, this one for X and Y direction. Similarly, sorry, the table is gone to the other side, so but the values here, that will be for 9, sorry, here of the negative moment coefficients. Okay, so for positive live moment 0.049, and for dead, that is 0.035. okay, for here dead 0.035, for live that is 0.049, and for negative that is 0.065. so for the X direction, so moment dead load, and from live load, span is X, in X that is 6 meter. So our total positive moment 14.93, and our total negative moment, that is 24.78. Similarly, for total positive moment, you can use the exact formula. Area of steel, that is 4517 millimeter square, that is greater than AS minimum. So we will provide AS. The spacing will be used number 10 at 130 millimeter center to center. Similarly, for negative moment, in the panel 1 X direction, for negative moment 861 millimeter square, that is greater than AS minimum. So here our positive moment, negative moment, negative moment is more, so that's why area of steel is coming more. So we will provide number 13 at 150 millimeter. Why? Its spacing coming too closer, so that's why we will shift to here number 10, 71 divided by 861 multiply with 1000. okay, you can see spacing is coming too small, 82 millimeter, so that's why shifted to higher number of bar, whose area is number 13, area is 129. So 129 divided by 861 multiply with 1000. Okay, answer is coming 149.85, so it is approximated to 150. So that's why number 13 at 150 millimeter center to center is provided. Similarly, in the panel X direction, we will calculate the panel Y. Okay, the positive and negative reinforcement. Here the positive moment is coming, here is the negative moment is coming. The area of steel, similarly for positive, that is coming number 10 at 190 millimeter center to center, and for negative, for the positive is here, for the negative that is number 10 at 190 millimeter center to center. Now similarly for panel 3, you will pick the coefficients and calculate the moment and calculate the area of steel. So here is the moment, positive moment, negative moment. So here is spacing, okay, for the panel 3 in the X direction. Similarly, positive moment, negative moment, area of steel in the Y direction. For the panel 4, where M is 1, K is 2, D 112 millimeter in the short direction. So M positive. So here again I will show K is 2, M1. K is 2, M1. So value are here. Sorry. .0.023, here 0.034, and here 0.041. Okay, for panel 4 X direction, 0.023, 0.034 and 0.041. This because the factors are same for the X direction and Y direction, so you can write same as for the Y direction. Whatsoever reinforcement will come against the positive moment, against the negative moment, you will provide in the Y direction also. So here comes the spacing, the negative. Okay, so when you have calculated the reinforcement for all the 4 panels, now you will go for the detailing of the reinforcement in the slab panels. So